One of the major uses of Taylor series is to approximate complicated functions with easy polynomials, and there is nowhere that this happens more often than in physics. It typically goes something like this. We use physics, laws, principles, reasoning to derive equations that will regulate the behavior of a system, but those equations are too complicated to do anything useful with them. So instead, we approximate those equations with Taylor polynomials, and then we can draw all kinds of conclusions. In this video, I'm going to present one example of something slightly different, where Taylor polynomials also help add light to a physical concept: kinetic energy. The kinetic energy of a particle is the energy it will have because it is moving, because it has a velocity. If you've taken a physics class, you're probably familiar with the classical formula for kinetic energy. The kinetic energy T is 1/2 of the mass times the square of the velocity. I've written mass at rest even though classically it doesn't matter. Mass doesn't change with velocity, because relativistically it will matter. Now in relativity, the formula for kinetic energy is quite different. You probably are familiar with Einstein's famous formula that says the energy of a particle is mc², where c is just a constant, it's the speed of light. But that is the total energy of a particle. The kinetic energy, the energy it has because it's moving, will be the total energy minus the energy it has at rest. So now I am distinguishing between the mass at rest m0 and m, that will be the mass when it's moving at velocity v. Now there is also an equation that allows us to write the mass at an arbitrary velocity in terms of the mass at rest, and when I use it, I get this. The mass is the mass at rest divided by the square root of 1 minus the square of the velocity over the speed of light. And that's all the physics I am going to use. Now these two expressions, even though they refer to the same physical quantity, are very, very different. This doesn't look at all like that. And yet there should be a relation between them. Well, relativity is the better model, but classical physics is a model that works perfectly fine when velocities are small. Or more precisely, I should be able to obtain the equations for classical physics from the equations for relativity as an approximation in the case that this variable is small. And that's exactly what Taylor polynomials were made for. And indeed, this expression for the kinetic energy is the smallest non-zero Taylor polynomial of this expression for the kinetic energy. That's the relation, and that's what I am going to prove. Here is once again the formula for the kinetic energy in relativity. I'm thinking of this as a function where v is the variable. So the part that depends on v and is complicated is this. So I'm going to isolate the essence of the function. The function is the minus 1/2 power of 1 minus the variable, where the variable is v over c squared. If this were my starting point, and I wanted to approximate this function with something simpler, what I could do is look for the Taylor polynomials for this function. And indeed, let's do that. The first Taylor polynomial, that could be simply the tangent line, could be the function at 0 plus the first derivative at 0 times x. And we can compute those values. The value of this function at 0 is 1, and the first derivative is minus 1/2, 1 minus x to something times minus 1. When I evaluate, I end up with 1/2 x. Now, instead of x, I have v over c squared, so the function I have is something like 1 over the root of 1 minus x squared, and in this case the approximation would be 1 plus 1/2 of x squared. So let's go back at the top and use this approximation. m0 c squared is simply multiplying. Now the first term is 1, but I have a minus 1, so it vanishes. So the next term is 1/2 of the variable square. The variable is v over c squared. That's it. And if you group those terms together, it will feel familiar. It is exactly 1/2 of m0 v squared. It's the classical expression for the kinetic energy. Success! So the classical expression is the first non-zero term on the Taylor series expansion of the relativistic expression, as it should be. Now let's say I want something slightly better, but not going full mode into relativity. Let's say I'm working with a range of velocities where the classical expression is already not being very good. But the velocities are not high enough that I need the full expression for relativity, and I would like to know, can I still get an approximation that is better than this one, but that it is not as complicated as this one? Well, of course I can. What I should do is, instead of taking the first polynomial, take the second polynomial. So the second Taylor polynomial would be like this one, but I need to add one more term, which is the second derivative at 0 over 2 factorial times x squared. So now take this function, take the second derivative, evaluate it at 0 and divide by 2. And if you go through that whole process, in this case, the coefficient is 3 over 8 times x squared. Or down here, for this other function, it would be 3 over 8 times x to the fourth. And now, let's use it here as well. I have to add one new term, the new correction, and that would be plus 3 divided by 8 of v over c to the fourth. And when I simplify and group everything together, this is... And I should correct something. I put here an equal, but this is not an equal. This is an approximated value. So what I have obtained here is the first relativistic correction to the classical expression for kinetic energy. This is the classical expression for kinetic energy. This is slightly better, and I could keep adding more terms if I need better and better values. Although at some point, it may be worth it to just use the original expression.